Okay, so I'm going to be talking about topological magnetic structures in biological systems, and this is going to be two pretty distinct talks. So I'm going to have an intro about topological magnetic structures, just some math briefly, and then I'm going to talk about what I did in my time in CU Boulder, where I made a topological magnetic structure where the order parameter was bacteria. And then I'm going to talk about my current work at MIT, where we're enhancing ion channel, which is like how biology feels stuff, manipulation through topology of nanomagnetic transducers. Okay, so topological structures, mapping from a parameter space manifold to a physical space manifold. The dimensions of these two spaces matter in what your topological structures are. Structures with integer topological charge can have enhanced stability, but not necessarily. Depends on a lot of things, depends on the order parameter. Most relevant, topological charge can be calculated as an integral over physical space. So for skyrmions, I'm sure we've all seen this. But this is a pain to do. So I'm just going to talk about how I kind of deal with calculating topological charge. So it makes things a lot easier for dealing with the structures I'm going to talk about. So you can parameterize your order. If you can parameterize your order parameter with this functional, which means that as you go radially out from your structure, you have a change in the z component of your spin texture. And as you go around the center of your structure, you have a change in the in-plane component of your spin texture. So this turns out to fit most skyrmions, most topological structures. And I'm going to give some examples. But yeah, it reduces this integral to a really nice thing, which is where theta is the angle between the z component of your magnetization and the z-axis, and phi is the in-plane angle. And so basically, just some brief examples of how this works, and it works really nicely. So for skyrmions, right, so we look at this is called the vorticity. This is the number of rotations your order parameter makes as you follow a closed loop around the center. So for skyrmions, our vorticity is 1. And then this component, right, we go from cosine 1 minus 1. So you get a factor of 2 from here. So 1 times 2 times 1/2 is 1 for skyrmions. So nice. I don't know if people have seen an n equals 2 skyrmion. This is an n equals 2 skyrmion. So if you do the same thing, if you go around a closed loop, you get 2 rotations of the in-plane component of magnetization. And so you get a n equals 2. Magnetic bubbles, there's no vorticity. So this component is 0, and you get 0. And then muon vortices, very similar to skyrmions again, except you don't have a full rotation of the z component of magnetization. So you only get a factor of 1 from this first term, so 1/2. So great, so we can really easily calculate topological charge for relatively symmetric spin textures. So I'm going to talk about 2D to 2D order map. Sorry, this is a 3-dimensional order parameter, right? Magnetization can point in any 3 dimension. I'm going to be talking a lot about 2-dimensional order parameters. So this is where your order parameter is confined to a 2-dimensional plane. And you can, again, parameterize it like this. And the skyrmion number is very easily calculated by the vorticity. So just some examples of this, right? Whirlpools in water, this is the velocity, the order parameter is the surface velocity vector of the water. Spin ice, this is, right, you're in these spin ice systems, your magnetization is confined to plane, and when they're all pointing in or all pointing out, that's your monopole. And then ants and deer can also form topological structures. So deer do this as like a protective thing. The deer in the center are the younger ones. The ant one is very particularly interesting because this is called an ant death mill, and I would argue that this is actually a topologically protected structure. The ants will go around and around in this circle until they all die. So yeah, so it can happen in some weird systems, and that's what we're going to be talking about. We're going to be talking about magnetotactic bacteria, specifically Magnetospirillum magnetotacticum. Magnetotactic bacteria are bacteria with magnetosomes, which are magnetite or iron silica organelles. So I kind of have a little figure here where I've drawn, my red arrows is my magnetization. And if you look at my TEM image, these little black dots are the magnetite nanoparticles. And they self-propel themselves with their flagella. Biologists think that they do this because they need to get to this very specific oxygen-rich environment. And basically, so I didn't know this either. The Earth's magnetic field in most places is like at a 60-degree angle. So it reduces a 3-dimensional random walk into a 1-dimensional random walk, and they can get to the appropriate oxygen environments better. OK, so the problem is biologists haven't been really great at explaining what's happening how these guys interact with magnetic fields. In rotating fields, it's really well explained, and there's a reason why this. But in uniform fields, they apply a field in the x direction. And basically, they're like, oh, all the bacteria go in the x direction. But it's like, what about this? And also, this is your figure you're showing me, so I assume this is the best section of data you have. But yeah, you have this big off-angle direction. And then also, it's actually really well explained in field gradients. But field gradients are boring, right? If I had just magnetic iron oxide nanoparticles in water, field gradients do the same thing. But yeah, I have to deal with this a little bit. But I'm really interested in uniform fields because I'm not actually putting a force on the bacteria. The bacteria are self-propelling themselves. And I'm just kind of hoping I can figure out a way to like direct them. So the first thing I did was I just did a bunch of TEM of the bacteria. And the thing I noticed was that most of the bacteria basically had like lines of the magnetite nanoparticles going through them. And then some of them didn't have any bacteria, or they had magnetosomes, or they had like weird clusters of magnetosomes. But we're going to be talking about what I'm calling aligned uniaxial bacteria, which composed 84% of what I measured in TEM. And the way I started approaching this was by doing micromagnetic simulations in MUMAX. So I started to simulate the magnetosomes in the bacteria. And I did a lot of simulations where I varied shape, spacing, and number of magnetic nanoparticles. So I also did different types of simulations where I did like LOG relax in order to get the lowest energy state of the magnetosome chains. I looked at a fixed bacteria, its anisotropy essentially, right? So it changed its angle relative to magnetization. And then also I did a rotating bacteria in a field. And basically there's a couple of things we can draw from this. So I kind of already suspected once I have a bunch of magnetic nanoparticles in a line, it's going to behave like a uniaxial ferromagnet. This is true. So magnetization will point up or down the chain of magnetosomes. And then in liquid, the bacteria is rotating, right? So in liquid, the magnetization will always align in the external field, right? That's the difference between the fixed bacteria and the rotating bacteria, is the rotating bacteria, I only have one energy minimum, where it's aligned with the external field. Okay? So I can make some predictive behavior. The bacteria's forward direction is at an angle relative to the applied field determined by the angle between its internal magnetic dipole moment and the bacteria's natural forward direction. So that really readily explains this weird behavior shown here, right? My bacteria's forward direction is this way, but my magnetosome chain is slightly off axis to its forward direction, so it's going to go in this weird angle. Great. So the other thing is that for uniaxial aligned bacteria, there's a degeneracy between whether or not the dipole chain is kind of pointed towards the forward direction of the bacteria or the backward direction of the bacteria. So we would expect in a uniform field the bacteria would equally likely go in either direction. And then, yeah, that's a figure for what I just said. I didn't click ahead in time, but yeah. So right, so we can say that I'm going to be talking about type 1 and type 2, where my dipole magnetic moment is aligned with the forward direction or aligned or anti-aligned with its forward direction. And then type 0 bacteria where they're not aligned and they can go off in like a weird direction, you know. So yeah, so we're not going to be talking about type 0 bacteria. But basically, so in order to do this, an experiment, we have microscopes, we have electromagnets, we have 3D printed holders to put my slide in an exact place. And I'm using these 200 micron thick bitty slides. So yeah, so this is hopefully a video that's going to play. Nope, everything crashed. OK, that was my fear. Yeah, so this is just going to have to happen like this. I don't know why. I was worried about this. But we're going to play these videos, and then we're going to go back into presentation mode. So yeah, so this is the video of the bacteria in a uniform 50 millitesla field. And you can kind of see they're going like this. But you know, saying kind of see doesn't really mean anything. I can do image tracking, particle tracking, right? So and what I found was 86% of the movement is in a 30-degree cone, which agrees really well with the 84% of bacteria I measured in TEM that should do that. And half of the bacteria were going in the plus x direction, half the bacteria were going in the minus x direction. So now we have a well-defined nonpolar velocity vector for bacteria of type 1 and type 2. And then one more video that causes my computer to crash sometimes, which is this one. So this one is I have put in the bacteria in a uniform out-of-plane magnetic field. And the reason why I did this was to basically show so what happens is I'm inserting a magnet in this video midway through, and it arrests the motion of the bacteria. So the bacteria were moving around, and now they're aligned out of plane. You can't see it all. Nobody can see. OK, so great. So I'm telling you they're moving around, and I put an out-of-plane magnet, and then they're aligned out of plane. They stop moving. This is really important because this shows that the bacteria's velocity vector in this slide is a 2D order parameter. OK? Great. OK, so this is the last terrible thing video that's happening, and then hopefully I can go to presentation mode again. Great. OK. So my idea was, OK, let's put them in the thin slide, apply magnetic field, and wait. And what I predict will happen is I'll get a buildup of type 1 and type 2 bacteria on the different edges of the slide. And that's exactly what happened. And so now I can, so you probably can't see this one, I'm guessing. Hopefully you can see this one. Hopefully this doesn't cause my computer to crash again. OK, I'm sorry, people. Yeah, we're just going to have to play this video. This one should be very visible. So we got a big swarm of them all moving around, and they came off the left side. And the ones that aren't moving are dead. Yeah, so great. OK, so. And yeah, so also, yeah, I was able to control individual bacteria of different types by isolating them. And I was at CU Boulder, so I wrote C and U. This was done manually, right? I'm controlling the electromagnet manually. And this was done with a pre-programmed sequence in the electromagnet where it went 0, 90, 0 again, or minus 180. And then, yeah, so what I did was I placed the bacteria in a thin slide with 4 magnets all pointed inward. So what you're seeing underneath is the analytically calculated magnetic field. And then what you're seeing on top is I'm doing an angular average of the nonpolar velocity vector over 400 by 400 micron squares. And so these black lines are the experimentally measured average nonpolar velocity vector. And in the center, we didn't have any average. Basically, we had a uniform mode. And so basically, yeah, we're able to generate a nonpolar skyrmion in the bacteria. And so I was pretty happy about this. And then I'm going to show you guys. Oh my gosh, I'm so afraid of videos now. OK, great. So yeah, so I was able to kind of see. So in the center of the slide, right now we have a field gradient. There weren't as many bacteria. But if I kind of go out, I could qualitatively show a video of the bacteria aligned with the relative structure of the skyrmion. Not able to do it in this direction because the slide's thin in that direction. And then I kind of cheated to generate a polar skyrmion because I was leaving this at the lab at this point by threading a wire through, oh my gosh. Oh my gosh, I'm so sorry, guys. Yeah, so I was able to generate nonpolar skyrmion through threading a wire through it. But yeah, we're done with this. That didn't make me happy. So now we're going to talk about enhancing so topological structures in the living order parameter are done. Sorry about the videos. And now we're going to talk about using topology to enhance magnetic nanotransducers for biological manipulation. So magnetic fields penetrate really well into biological tissue because magnetic fields don't interact with most biological structures. I just showed you guys a bunch of biological structures that magnetic fields interact with, but that's not normal. Most biological structures don't have anything magnetic in them. But yeah, so for the same reason that they penetrate really deeply, we don't do anything with the biology. So we need something that converts magnetic fields into a signal that protein membranes, specifically ion channels, can feel. And we do this through nanotransducers. So the first nanotransducer I'm going to talk about are magnetoelectric nanotransducers. And they're composed of a magnetite core. And basically, the magnetite core is magnetostrictive in an alternating magnetic field, right? So we have, this is the multiferroic triangle. So we can have a magnetoelectric material where the dipole moment and the magnetization are directly coupled. Or we can kind of go around the triangle in a weird way. So we can have a magnetostrictive core. And then we coat it with barium titanate, which is a piezoelectric material. And so we can get an artificial magnetoelectric by going around the other side of the triangle. And that's what we did. And my job was to basically figure out to kind of try and enhance the magnetostriction to improve the generated voltage. So magnetostriction is realignment of dipoles, and it's really, really highly dependent on crystal structure. And you can kind of have two versions of magnetostriction. But basically, right, so this is the full version of the equation for magnetoelastic force. And I can't really change the B1s and B2s. Those are determined by material parameters. So if you're a new material person, doing DFT, please let me know what the good things are. But I can change the spin texture, right? And kind of my thought was, OK, like it's really important we have non-uniformity in the spin texture. All these terms are derivatives. And if kind of like, I work with non-uniform spin textures, let's make something that's non-uniform. So we made the disks appropriately sized to generate a magnetic vortex or a muon. And when we did that, then I put them into Mumax magnetoelastic simulations to compare to isotropic particles. So these are not magnetization maps, what you're seeing. These are displacement maps, OK? So this is displacement. And basically what we found was just from going to an isotropic particle to a particle with a vortex state, we got a 3-fold increase in the magnetostriction, which is great. I actually kind of disagree with this. This is the engineering version of this. There should be, like, I think, a factor of 2 difference. But I'm in an engineering lab, so this is what's being produced. So great. So the vortex state enhances the magnetostriction by like 2.5 orders of magnitude, which is awesome. But then we had an additional problem, which was basically that in order to grow epitaxial barium titanate shell on this, we needed to have like a mediator, which ended up being cobalt iron oxide. And we wanted to know how's this going to affect the magnetostriction. And I kind of suspected this is going to be great because there's some work done where it shows that if you have interfaces between different magnetostricted materials, you get enhanced magnetostriction overall. And that's exactly what we saw. And we got an order of magnitude increase in this. OK, so then what we did was we injected the magnetoelectric nanoparticles into the mouse's ventral tegmental area, which is where dopamine is released. So dopamine makes you feel good. And this was the setup for doing fiber photometry. So the mouse is in this, and you have a fiber in its brain, and you're really directly measuring the electric signal you're doing. But we're not going to talk about that. I'm just going to talk about the result, which is basically what we did was we did a behavioral modification assay. So we have the mouse in a chamber where it has 2 coils, and basically only one of the coils is on. And what happened was at the start of these tests, the mouse actually doesn't like the coil that's on because it's slightly vibrating from inductive forces, and it doesn't like it. But if you look over here, what you see is after 5 days in the chamber. So actually, this is really interesting. So on day 5, we don't have the field on anymore. So day 1, 2, 3, 4, we have the field on in this chamber, so it's eliciting dopamine response. And then on day 5, we turn it off, and the mice really strongly still prefer that other chamber. So this is the first in vivo, so in a living animal experiment doing dopamine release. And this is brought about by enhanced magnetostriction of neurons, because the problem was previously if you injected the amount of nanoparticles you needed in order to elicit a response from the VTA, you would kill the mouse. So we needed to reduce the concentration, and this enables this through the vortex state. OK, so now I'm going to talk about one more nanotransducer, which is a thermal nanotransducer. And so, we can have thermal ion channel activations. Also, thermal nanotransducers can be used to kill cancer. This is actually translationally happening in Germany. Like people get magnetite injected into cancer tumors, and then they heat the magnetite and kill the tumor. So I'm going to present one conventional model of the physics of the thermal nanotransducers, which basically you have an anisotropy energy barrier, you have a uniform magnetization, and the theory is, you push your uniform magnetization over an anisotropy energy barrier. So you go from a low anisotropy energy state to a high anisotropy energy state to a low one, and all that energy is assumed to have gone to heat. And basically, it turns out that this is proportional to hysteresis loop area. And it's dependent on a uniform m and its magnitude. So great. I have some problems with this. The first problem is requires uniform m. This whole conference is about non-uniform magnetized materials. So that's really a big problem. And also, where's symmetric exchange in this? What's the role of symmetric exchange in the heating in magnetothermal nanotransducers? That's really, really important, right? That's what makes a magnetic material magnetic material. So I kind of like went to the LLG, thought about it, and also some guy analytically calculated in 2009 the dynamic switching of an ellipsoidal nanoparticle, and he made magnetic Feynman diagrams. So if you've ever thought I'm missing Feynman diagrams, this is your book. And the result is really unsurprising, which is that your energy losses is proportional to the basically the changing magnetization of each spin times its damping constant. And this is just like velocity-dependent frictional energy losses, right? Like if I throw a baseball, the energy loss is very similar to this. It's dependent on v squared times some constant. So on a very fundamental level, heating is induced by rapid movement of individual spins driven by exchange. Okay, so how am I gonna kind of probe this system? Do an experiment to figure out this. So just a really simple Gedunken experiment. If I have just two magnets magically antiferromagnetically coupled, and I have them in an alternating field, and I do my hysteresis loops, and then I look at the total hysteresis, right? The total hysteresis has a factor of 7 less area than the subloops of the individual magnets. So kind of with a uniform M, you have to you're underestimating your heating by a significant amount. There's real systems like this. Ferrimagnets are like this, right? So I wanted to look at the heating of gadolinium cobalt ferrimagnets, and you can tune the magnetization in these by determining the ratio of the two elements, so gadolinium and cobalt. And basically, if conventional theory holds, then these systems don't heat. If nanomagnetic theory holds, then these systems do heat. So I made them in colloidal solution, right? I did photolithography and then released them into water and then transferred them to isopropanol to prevent them from oxidating. So this is them in solution. And then I did hysteresis loops, right? So on the left is the gadolinium cobalt disks. On the right is a standard heater magnetite. And what you're going to see, this black box is this entire graph, right? So this is 2 orders of magnitude less magnetization than the normal magnetite nanoparticle. And if I calculate the energy loss in the hysteresis loop at the fields I'm going to be driving them at, it's, again, 2 orders of magnitude difference between the predicted heating in these systems. When I measure it, I have a factor of like 2, 3-ish. So something's up. And how do we explain this? This is my calculated SLP versus the measured. Specific loss power is the term used for the heat given off. So we have a fiber, it measures heat. So I can calculate the area of the subloops because I have 2 coupled equations, and I know the area of my big subloop. Basically, I can figure out, I just have 2 coupled equations, blah, 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 solve them. I get the relative sizes of my subloops compared to the total hysteresis loop. And then what I can do is I can calculate the area of the cobalt lattice and the gadolinium lattice separately, and then I can add them together, and we have really good agreement now between my calculated heating and the experimentally measured heating. So heating is induced by exchange-driven rapid movement of individual spins, and this is supported by, we're doing vampire simulations on these systems. But why am I talking about this system, particularly at a topology conference? It's because I think in the future, I don't know if I'm going to get to this, but skyrmion collapse is some of the fastest exchange-driven dynamics available. So I think that it would be really interesting to look at a system where I have skyrmions collapsing versus a system where I have bubbles or non-topological structures. And maybe in the future, but not right now. And so I'd like to thank my group and all my collaborators, particularly Jeff Beach and his group for growing the gadolinium cobalt. And that's it.